so thank you for coming. Also, thanks for having me here. I forgot to thank the organizers yesterday. Thanks for putting this together. It's really a pleasure and an honor to be in Cambridge. The trees are very beautiful. The sky is very gray. You can say that too. Okay, so today's continuation of yesterday's quantum information kind of crash course will be hopefully lighter, and we will see lots of examples. And so again, I kind of suggest that you relax, kick back. And so I'd like to put into action several of the ideas that we saw yesterday. And the first of which is, so I'd like to talk about correlations first. And so what is a correlation? Correlation is a relation between two entities, or more precisely, like let's say two, if it's a bipartite correlation, right? Between various degrees of freedom, by which, if you find out something about one of these degrees of freedom, you can infer something about the other one. Okay. If that is the case, you say that they are correlated. And this can be measured in various ways. Maybe a standard way would be with the mutual information. So we will say that two systems are not correlated if by finding out what the state of one of these systems is, you don't know anything about the state of the other system. But if they are correlated, they can be correlated in a stronger form. So there are various kind of degrees, right, to how strongly correlated they might be, or what kind of correlations they exhibit. In particular, we will distinguish today between classical and quantum correlations. Okay? So you might be able to say just something with a great deal of uncertainty about the other system. That would be kind of a weak form of correlation. Or you might be able to assert with certainty what the state of the other system will be. That would be a strong form of correlation. So pure states can contain quantum correlations, which means entanglement. Some people call it quantum entanglement because you can also use the word entanglement in plain English to mean like tangled, right? Mixed states can contain classical and quantum correlations. And that's what we're going to see now. But in either case, we will only consider bipartite states here, that is to say, between two parties, where the analysis will be extremely simpler and not representative of the analysis of multipartite entanglement or correlations. That is, in some sense, I believe it's a fairly general lesson that 2 is special, like especially simple. And that what works for 2 very rarely generalizes to more than 2, but it's still kind of our stepping stone. It is a case where we can do a fair deal. So we will only consider bipartite states. Okay, so let us first consider pure states. And where, as I said, we can only have quantum correlations or entanglement. And in this case, the story is wonderful, because for bipartite pure states, you can tell it all with a Schmidt decomposition. And in physics, people call it the Schmidt decomposition, but in math, really, it is nothing but the singular value decomposition. So this Schmidt decomposition measures the entanglement of the state as follows. So,
just a question. So, just to make sure, bipartite, it always would mean that it's a state of a tensor product of two Hilbert spaces, right?
Yes.
Okay.
So bipartite means two parties. And that's a nice comment, because whenever one talks about correlations, they are always relative to a splitting of the degrees of freedom. In this case, a bipartite splitting, but entanglement only makes sense with respect to a distinction between the Hilbert space attached to Alice and the one attached to Bob. That is a choice of the user of the theory. Okay, So the Schmidt decomposition goes as follows. Any bipartite pure state, psi, this is a ket. Remember, it is a column vector, which I'm taking to be an element of CD, tensor CD, normalized in the 2 norm. Sometimes I would write psi sub AB to emphasize that it is for both systems. In this case, I am omitting that. Can be expressed as psi is a sum over an index k, say running from 1 to r, of some coefficients lambda k, which are positive, and then a vector on the Hilbert space of A, uk, say, tensor a vector on the Hilbert space of V, say vk, where the lambda k's are positive and called the Schmidt coefficients, and they satisfy that the sum over k of lambda k squared is 1. This is coming from the normalization condition of the state. And then the set of uk's, so this is a set where the index is k. This set is a set of vectors that are orthonormal. Right? So each of them is normalized, and if you take the inner product with a uk times ul, that's delta kl. So these are orthonormal, and the vk's, so on Bob's side, are also orthonormal among themselves, okay? The uk's with the uk's and the vk's with the vk's. And the minimal such R, which is the number of summons, is called the Schmidt rank of the state. So this claim is proven by doing a singular value decomposition of the matrix of coefficients obtained from expressing psi in any product basis. I guess I'm not sure if it should be an orthonormal basis here. It should be a product basis. So for example, express psi in the computational basis. Remember that we had the computational basis for a single system, and I didn't mention that it is clear that by taking the tensor product of the computational basis on either system, that is a basis of the whole of the composite system too. So this is what I am doing here. It's a resolution of the identity I, comma j. I'm quite inconsistent with the commas. Sometimes I write them, other times I do not. It doesn't mean anything. And sometimes I write the tensor product in between, other times I omit them. I think that's quite common in quantum information. In this case, so here you see that the I is like the basis for system A, JJ is the basis for system B. They are two resolutions of the identity independent of each other. And I am expressing my state psi in this basis. And this gives me a matrix of coefficients Mij. These are complex numbers, right? They are the entries of psi in this basis. And now I view M as a matrix where I is the row and J is the column, and do a singular value decomposition of M. Every matrix admits a singular value decomposition. So an expression of the form U times delta V, where U and V are unitaries, and delta is diagonal and positive semi-definite. So that is to say that the diagonal elements are obviously the singular values. So in components, I have that the Ij is of this form. It's a sum over k of U, Ik, delta k, Vkj. And R is the number of singular values, like non-zero singular values. And these are precisely these lambda k's. The Schmidt coefficients are the singular values of my matrix M. And now flagging this in here and identifying here as my new vector UK, and this here as my new vector VK, I obtained a Schmidt decomposition. And then just note that this is a unitary transformation on an orthonormal basis. So this results in an orthonormal basis. So I should have started from an orthonormal basis as I did here with a computational basis. And the same is the case here. Yeah. So, and from the normalization, I obtained this condition. So an immediate implication of the Schmidt decomposition is that if two systems A and B are in a pure state, that is to say, okay, I think my notation is really quite inconsistent with Robin's, but at least mine hopefully is consistent with mine from yesterday. So, so please, only keep in mind mine from yesterday, just to follow these symbols. So, say that the density matrix is in a pure state psi. Then, from the Schmidt decomposition, it follows that the eigenvalues of the reduced density matrices, rho A and rho B, are the same and are nothing but the squares of the singular values, or of the Schmidt coefficients. Okay, so again, if rho is in a pure state, then the partial traces, like the reduced density matrices, have the same eigenvalues and are the squares of the Schmidt coefficients. This you can see here. So the eigenvalues of rho A and rho B are equal and given by the squares of the Schmidt coefficients. And to see that, well, for example, to obtain rho A, take the partial trace over psi, and because those V's were orthonormal, that immediately results in a spectral decomposition of rho A. And the same with rho B. In this case, the UKs are orthonormal, so you get that they have the same eigenvalues, but different eigenvectors, different projectors. It's only true if the global state is pure. Now, that's a definition. A product state is pure, a pure state is product if it can be written as A tensor B for some A and B. And that's the comment I made earlier. So a pure state is product with respect to a certain splitting of the Hilbert space. Okay. Right. Okay. And now let us define, as it is usual in quantum information, a state plus as 1 over square root of 2 of 0 plus 1. So in the computational basis, it's like 1 over square root of 2 of 1, 1. And the state minus is 1 over square root of 2, 0 minus 1. So it's like 1 minus 1. Okay? This is like the Fourier transform of the computational basis, which, if in the simplest case of qubits, is given by the so-called Hadamard gate. If you've heard of it. And this plus and minus are the eigenstates of the sigma x operator, or x operator that we saw yesterday, which is the flip operator, right? Note that if I apply the flip operator on the state plus, I get back the state plus. So plus is an eigenstate with eigenvalue plus 1. If I apply the flip operator on the state minus, I get minus the state minus. So minus is an eigenvector with eigenvalue minus. Okay? Okay, so now let us see lots of examples. So a product state, for example, is 0, plus, or 0 tensor plus. And if I find out what the state of Alice is, namely 0, I get no information about the state of Com. Another product, yeah.
Could you please say something again about what you mean by entanglement is defined with respect to a bipartition of degree freedom?
Yeah.
What is?
Well, there is a composite Hilbert space. There is the Hilbert space where the state lives, and it could be split into HA tensor HB in different ways. In this case, it's so simple that there's only one non-trivial way, because it's like C4, so it's like C2 tensor C2. But generally, if you have, I don't know, several photons and you're describing their polarization or other facts, it depends on what degrees of freedom you're talking about. Also, purely mathematically, it depends on what part of your, so what Hilbert space your HA is and your HB is. And every talk about correlations or lack thereof is a statement with respect to that splitting. And the statement could be completely different for another splitting.
Yesterday you said degrees of freedom have everything to do with observables.
Has everything to do?
I mean, yesterday you said that degrees of freedom are like observables. Yesterday there was a statement that you...
So yesterday I said that the closest analog to a bit in quantum theory is an observable of dimension 2, like of a qubit. This way of introducing a qubit is very non-standard, and I took it from David Deutsch. That's what makes sense to me. Yeah, okay, so an observable or a Boolean observable is, I think, what I said yesterday. Is that fine? Okay, so another product state is the following. In C2, tensor C2 again, so I am using here the computational basis, and this is rotated with a certain angle theta, tensor, another state rotated with an angle psi, and here there is a relative phase gamma. Okay, that's another example of a product state. A pure state is entangled if it is not product. So examples of entangled states are the following. 1 over square root of 3 of 0, 0 plus I 0, 1 plus 1, 0, or something like some normalization constant times 0 plus minus 1 over square root of 3, 1, 0, or 1 over square root of 2, 0, 0 minus 1, 1. This state appeared yesterday. It is what we called phi minus. That is a Bell state, this last one. The statement is that these are entangled states because they are not product. But you should be aware that, so a state is product, or a state is product if there is some A and B such that psi equals A tensor B. And it is entangled if there is no such A and B. So presenting just one decomposition of the state does not suffice to convince anyone or to reach a conclusion that it is product or entangled. For example, this one a priori might seem to be very entangled because it has 4 terms, right? 1/2 of the four possibilities of the computational basis. However, there are too many of them somehow, because in fact it is nothing but plus plus, which is a product state. And on the other hand, I don't know, take this one. Well, here you can take kind of common factor of 0. This is also a product state. But this one is entangled. Again, the last one is psi plus. It is a Bell state as well. And fortunately, whether a pure state is product or entangled can be determined with a Schmidt decomposition. So a state is product if and only if its Schmidt number R is 1. You might remember that the Schmidt number is the minimal number of terms in that sum of lambda k, uk, tensor vk, right? The statement says if you have one term it is product. If you have more than one term, it is entangled. The proof is immediate. So we're really lucky here. We have a full characterization. It's if and only if, and it's really simple to compute because doing a singular value decomposition is very easy. This situation is by no means representative of the general one.
Because
Yeah.
this observation, so it's clear that if R is equal 1, then you have a product state.
Yeah.
Is there a quick way to see the R is 2?
Yes. Yes, you have at least two terms. And reduced density matrices have like eigenvalues. Yeah, I think we will go there also. Okay.
Sorry, this was a quick question. So before, so in this observation and everything we're doing, it's all when we have fixed a like tensor decomposition on the original space.
Yeah.
So we have a fixed HA tensor HB, and it's with respect to
Yes.
like basis of these two and so on that we can call this.
Yes. Not only that, but any notion of a correlation is with respect to a splitting, or with respect to two parties. Okay, but after saying that it's wonderful, I want to say, present a shortcoming if you want, and it is the fact that it's not continuous because it's a rank, right? So, for example, take again our favorite state, the Bell state phi plus. Its Schmidt rank is 2. And we said yesterday it's maximally entangled, so that's fine with us, right? But now take this one with epsilon very close to 0 yet non-zero. Well, this is very close to the 0, 0 state. It's not normalized, sorry. I forgot to normalize it properly. Instead of 1 over square root of 2, you know, there should have been an n, a proper n, yeah. Okay, so the second state is really close to 0, 0. So there should be a way of, so it's very close to a product state. However, its Schmidt rank is 2. So the Schmidt rank does not allow us to distinguish the fact that the first one is very entangled and the second is very little entangled. Which motivates the introduction of the entanglement entropy. It's a better measure of entanglement. So given a bipartite state, psi AB, the entanglement entropy, so this notation is very ugly, and I'm sorry about that. I never liked it, but I don't know how to go around it. But let's do that. So E of psi of AB, okay, is given by the von Neumann entropy of the reduced density matrix A, equivalently of B, because so the von Neumann entropy is minus the trace of rho A log rho A. So I'm not specifying the basis of that logarithm. I'll go there in a second. I think sometimes people take it in base D, where it is the dimension of rho A. Other times it's always base 2. And because rho A is positive semi-definite, the von Neumann entropy is just given by minus the sum over I of lambda I log lambda I, where lambda I are the eigenvalues of rho A. So it's like the Shannon entropy, where the probabilities of the random variable in the classical case are replaced by the eigenvalues of the density matrix. So the statement then is that the entanglement entropy of a bipartite state is given by the von Neumann entropy of the reduced density matrix. Yeah.
So here, eigenvalues of rho A is sort of like squares or the square roots of the Schmidt coefficients from earlier, right?
Yeah, exactly. That's why I said it doesn't matter if you take S of rho A or S of rho B, because the eigenvalues of rho A are the same as those of rho B and are the squares of the Schmidt coefficient of psi. So again, please digest that for a second. We are saying that a measure of entanglement of a bipartite pure state is given by the entropy of the reduced density matrix. And the entropy is a measure of uncertainty, or a measure of disorder, and like in a classical variable, right? So that is saying that if there is a lot of entropy in the reduced density matrix, as in a lot of uncertainty, that is a sign that it is sharing lots of information with the other degree of freedom. In other words, that the global state is entangled. We will see examples of that. In other words, if this half of the system, rho A, has no uncertainty, that means that it is not sharing any information with the other half, so the entanglement of the global system will be 0. So a state psi is product if and only if this entropy of entanglement is 0. So for one direction, well, if it is product, then it can be written like that. So rho A is a rank 1 matrix, so the eigenvalues are 1, 0, 0, 0, so the entropy is 0. And there's just this little thing that you need to use, this limit, to get the value right. For the converse direction, now we come to, I think someone asked about this earlier. First note that this entropy of entanglement is non-negative. If it is positive, then rho A must have at least 2 non-zero eigenvalues. Let's call them lambda 1 and lambda 2. Since they are the square of the Schmidt coefficients of psi AB, well, there you go. This has R at least 2, so it is entangled. Okay, now, this is a little comment about the base of the logarithm. If it is if rho A is an n times n matrix, and we take the logarithm in base n, then the entropy is normalized in the sense that it is at most 1. And just recall that the maximum of S is obtained for the flat distribution, right? If you have 1 over n for all n, then, so rho A in some basis, in its eigenbasis, is given by that, so it maximizes this function. And yeah, so one definition of a maximally entangled state here is a state such that the entropy of entanglement is 1. Okay, let's see examples. Okay, so let's do some sanity checks. Okay, make sure that this is sensible. So if you have a product state 0, 0, by the way, 0, 0 has no correlations. This is often a discussion that comes up in dinners or something. If you have the state 0, 0, no correlations, okay? Because if you find out that the state of Alice is 0, there's nothing you can tell about the state of Bob, okay? Okay, so this is a product state, and the reduced density matrix is the projection onto 0. And so, because it's a rank 1 thing, the entanglement entropy is 0, as you would expect. No correlations. Let's take the singlet, 0, 1, minus 1, 0. Oh, this Bell state has a special name in physics called the singlet. All right, so for the singlet, the reduced density matrix is maximally mixed. It's a normalized identity. So the eigenvalues are flat. So the entanglement entropy is 1, so it's maximally entangled. By the way, I forgot to mention that this, yeah, that's coming now, that this is continuous, yeah. Let's take the example from earlier, properly normalized. 1 over n, 1 minus epsilon, plus epsilon with this normalization. Then, yeah, the reduced density matrix is given by that. So the entropy of entanglement is positive at very close to 0 and would go to 0 as epsilon goes to 0. 2 is special and very misleading. The first observation is that this wonderful Schmidt decomposition only works for bipartite systems. To the best of my knowledge, there is no analog for 3. So you need other measures. There's kind of a zoo of other measures, ranks, other things you can do for tripartite. Okay, let's now go to mixed states. So I want to distinguish various cases. The first case is the one in which there are no correlations. So I will say that a mixed state is product if it can be written as sigma A tensor tau B for density matrices sigma A and tau B, right? So this sigma A and tau B need to be positive semi-definite themselves and also normalized. They contain no correlations, again, because there is no observable that you can measure on A that would give you some information about B. For example, okay, 0 and 1, 0, 1 is a product density matrix. So is the normalized identity. And so is something like that. So is plus plus tensor 0, 0. That is not a valid decomposition because Z, as you may remember, is like 1 minus 1. So that's not a density matrix. It's not positive semi-definite, right? So of course, beware. If you can put the minus sign somewhere in there, everything changes. Like the whole analysis is nonsensical. So this is not a density matrix. But now let's take this one, which we will encounter later. That's not a product density matrix. Because you cannot write it as the tensor product of something only on A times something only on B. You need at least 2 terms. And that is the decomposition with 2 terms.
Can you please explain why there's no correlation? Because
there's no correlation? No, there are correlations. This is not a product density.
oh, okay, so there are correlations.
Yeah, yeah, that will be kind of our key example in 5 minutes.
Sorry, I'm a bit confused about the terminology. So would you scroll up like to see if there's sentence? So when you say here, because previously we were talking about this states or vectors, and here we're talking about density matrices.
Yeah, because
So
I
here-
moved. Yeah, I'm sorry if that caused confusion. I moved from pure states, which are represented as vectors, to density matrices, which are represented as matrices. And kind of the punchline of the story is that pure states can only contain quantum correlations, but in mixed states there can be classical, quantum, or both correlations. So I'm trying to distinguish these 3 cases.
And so really, like, I guess, everything for the pure states we could have gone for the correlation matrix you could get from it as well. And
Yes.
It's just a rank 1.
Yeah.
And here it's a correlation matrix.
Yes. That's coming next. Yes, you're right. Okay, so if on the other hand, here you take like all summons, well, at first you might expect there are so many summons that this will not be a product density matrix, but in fact, if they are all taken with equal weight, well, it's nothing but plus plus tensor plus plus, so it is a product density matrix. There might be other weights, right, so that this trick also works, but at least with equal weight, it is a product density matrix. In the second case, so I wanted to do that a little more carefully. So, classical correlations. Okay. So imagine, I wish I had them, but I don't, unfortunately. Imagine that I had 2 boxes, opaque, and I had balls of 2 possible colors, red or blue. Okay, and behind a curtain here, I put 1 ball in each box, and then I come out like a magician, and you only see the boxes, okay? But I promise that the 2 balls are of the same color. Okay. What density matrix do you use to describe your state of knowledge? Oh, sorry. And I also promised that I put either color with equal probability. So what density matrix describes your state of knowledge? I claim this one. 1/2 of, so this is like the degree of, the color is the degree of freedom here, right? Of red, red, tensor red, red, plus 1/2 of blue, blue, tensor blue, blue. Okay? So the point of the story is that this is a classical correlation in the sense that the balls are of a certain color, but the state is just describing what you don't know, right? In this case, revealing the color of the box will make you update your state of knowledge, but it would not change reality, or like the reality of these balls, or of that property of these balls would not change, or that's what we would commonly agree that is the case. By the way, that's also a clear example of what it means to be a correlation. If you only open 1 box and you discover it's red, you can infer that the other box is also red without ever examining the other box. That is, of course, provided that you trusted my initial promise.
Can I ask a question?
Yeah.
Will you say something about what happens to the classical correlations when you use state purification?
Yes. Yeah, and obviously this state is reflecting the promise that I will never put a red and a blue ball or a blue and a red ball. Maybe another example is again with, say, my socks. If I have black and white socks and I promise that I always wear socks of the same color, and that, I don't know, 3/4 of the day I wear black socks and 1/4 of the days white socks, you could represent your state of knowledge about the color of my socks today with a similar density matrix. And by finding out about the color of my left sock, you could infer what the color of my right sock is. So, okay, now, a mixed state is separable if it can be written as a convex combination of product states, which is the same as writing it as a convex combination. So this is a sum over J times Pj. Pj is a number that is non-negative of a density matrix on A with an index J times a density matrix on B with an index J. Okay? So note that such a state is positive semi-definite. But not every positive semi-definite element on a tensor product is of this form. I think yesterday I made this comment. If you take a tensor product of a Hilbert space times another, then you consider what's positive semi-definite on this tensor product. Some of the elements will be a convex combination of what was in the cone here times what was in the cone here, but not all of them. Separable states are precisely those that are a convex combination of what was in the cone here times what is in the cone here. Okay, obviously it's crucial that the PJs be non-negative. Any state can be expressed like above with a single PJ negative. It's also crucial that these things are positive semi-definite. And then a separable state only contains classical correlations, because you can see it as, well, this convex combination is like expressing your lack of knowledge due to the promise of someone, like the one I made earlier, right? Convex combination is expressing this ensemble that is reflecting your lack of knowledge. Actually, it's more complicated because the composition is non-unique, so I think this interpretation runs into problems because it's non-unique, but that's the best I understand it now. Okay, so examples of separable states, mixed states. This one is in essence the one with the red and the blue balls, or me wearing socks of the same color with equal probability and you not knowing what color I'm wearing today. Or that in another basis. I forgot to say earlier that plus and minus form an orthonormal basis of C2 as well. They are normalized and they are orthogonal to each other. Or such a combination, this would reflect if I say, look, I'm never going to put 2 blue balls in the boxes, but any of the other 3 possibilities are equally probable. Or, I don't know, something like that. That's similar to this one, flipping A and B. But I don't know, consider more examples. Imagine that here I don't know, plug in Z. Well, obviously that's not a valid decomposition. At this point, I don't even know if it's a state. There could be some cancellation of the negative eigenspaces. I don't think in this case it is so, but that doesn't bring you anywhere. Like this, you cannot tell anything by that decomposition. Or again, I think we've seen this several times, that's a product density matrix. It's not even separable. Okay, now case 3, that was asked before, only quantum correlations. We are back to what we saw earlier for pure state. So in this case, the state is rank 1. So we have perfect knowledge, but the entanglement entropy of psi is non-zero. Like, for example, phi plus the del state. Okay, now comes a really fun thing. Now this is pretty crucial, okay? So consider, or do you want to take a 3-minute break? Yeah, some people are saying yes. So, okay, maybe we reconvene at 12:04. Not yet, but it will be made available.
Okay.
You are freezing. Okay, so let's come a bit to the crux of the matter of these kinds of correlations. And so consider on the one hand, a state we've seen many times, that is to say a projection onto phi plus, okay? So remember that phi plus is like 0, 0 plus 1, 1. And so when you take the bra and the cat and the bra, you get that matrix. There are zeros. It's like a 4 by 4 matrix. There are zeros in all the slots that you're not seeing. Do you agree that that is the matrix representation in the computational basis of the projection onto phi plus? Do you agree or not agree? It's like you get all these cross terms like 0, 0, 1, 1 plus 0, 0, 0, 0, right? So do you agree with that equality up on top? No? So you have rho C, it's like 1/2 of 0, 0 plus 1, 1, 0, 0 plus 1, 1. So in the computational basis, you get 1, 1, 1, 1. Okay, right? Are you happy with that? So these ones are crucial. Are you happy with that? Is everyone happy? Yeah. Okay. On the other hand, let's consider the state we saw earlier about me putting the two balls in of the same color in a box, and you not knowing what color the ball was. And we agreed that a representation of that state of knowledge would be such a rho C, which is like a convex combination now of the projectors onto 0, 0 and 1, 1. So in the computational basis, that is that matrix representation. But we agreed that they are supposed to be interpreted, they are supposed to be represented very different things, radically different things in a certain sense. The first one contains only quantum correlations, because it's a rank 1 projection, but it's clearly rank 1, right? Like the first row is the same as the last row. You can also. The second one is rank 2. What's not clear just by the matrix is that it is not entangled, right? You can, but in fact, this decomposition proves that it is not entangled, because that's a convex combination of product states. And we agreed that the second one only contains classical correlations. So how can we distinguish them? Okay, so first of all, it turns out that in the z direction, which is the eigenstates of z are the computational basis states, remember? Maybe that's helpful. Can I write here? Can you see if I write here? No? Can you see if I write there? Okay, so Z in the computational basis is this one. So of course, Z on 0 is 0 and Z on 1 is 1, minus 1. And because it will appear in a second, X is 1, 1. It's a flip operator. That's called a flip. It's the only thing you can do to a classical qubit, flip it. What does it mean to apply Z to a classical qubit? It doesn't make sense. The 1 would get a phase. And X on 0 is 1, so it's a flip operator. X on 1 is 0. And the eigenstates are plus and minus. All right, so now you can consider an observable such as Z tensor Z, which is actually which we also saw yesterday, it's like 1 minus 1 minus 1, 1. And you can compute the expectation value. So, okay, what are the eigenvalues of Z tensor Z? They are 1 and minus 1. It's the product of the eigenvalues of each of them. So the expectation value of this observable Z tensor Z in row Q is maximal, like it's 1. So this means that they are perfectly correlated in the Z direction. The same is true for row C. They are also maximally correlated. This is saying the following. If I measure the first part in the Z direction and I obtain 0, I am sure that the second party will also be in the state 0. And this is true both for row Q and row C. So this observable does not allow us to distinguish between them. The magic comes when you change the direction. If you measure in a complementary basis, I'm not sure what complementary basis means, but in some sense it's like the maximally different basis, or like the eigenbasis of sigma y would also be maximally different, but we've done a kind of a Fourier transform from X to Z, okay? But if you measure in the X basis, then the correlations of row C disappear. It's one has to do this little calculation to see that this is true. This is saying that if I were to measure, remember my two balls, both red or both blue, if I were to look at the state of one ball in a different basis, it is unclear what that means classically. The best analogy would be that you look at it you look at a different property of the ball, maybe like the shape. Then in that basis, it would be completely uncorrelated with the state of the other ball. In contrast, if they were to share a maximally entangled state, if they were to be in the state row Q, they would also be maximally correlated in that basis. That is to say, the expectation value of XX in row Q is 1. So you could maybe think that the quantum correlation, if two states are in a quantum correlation, if two systems share a quantum correlation, it is as if they were correlated in different bases, or like for different properties simultaneously. Okay, so the general case is a row containing classical and quantum correlations, in which case, as you can imagine, well, rho is entangled if it is not separable. That is, it cannot be written as a convex combination of product states. And it is, if it is rank not 1, then it contains both kinds of correlations. For example, take this convex combination, 1/4 of the projector onto phi plus 3/4 of the projector onto phi minus, that contains classical and quantum correlations. But be careful, if you take such a combination, you know these are Bell states, so they are very highly entangled, but if you take a convex combination with equal weight, then the off-diagonal terms cancel, and you just get 1, 1, which is the rho C, is the state with only classical correlations. Yeah, it's very hard to determine if a mixed state is separable or entangled, and that can be made precise. It's not so easy to make it precise, but for some formulation of the problem as a computational problem, it is NP hard. Okay, so with that, I'd like to move to purifications.
I have a question. So given a state, is there some definition of amount of classical correlation?
I guess you could use various measures, like maybe the mutual information or stuff like that. I guess that kind of brings you into classical information theory. And
Yeah, because you can just say whether it's separable or entangled, but when it is entangled, how much of classical correlation is there, it is difficult.
Yeah, not sure exactly how to quantify. I mean, I'm sure there are many options, but I cannot give you one clean answer.
And the entropy from before, we extended to density matrices?
Yes, you can certainly, like, what kind of entropy? I'm not sure what it would tell you. Yeah, I guess the interpretations would be more dubious. I mean, maybe it's no longer so popular, but this used to be one of the main research areas, at least in the early days of quantum information, about 15 or so years ago. Like characterizing entanglement was kind of a holy grail, but it turned out to be very hard, in some sense formally hard, not unique, and the multipartite world is, well, some people still do work on that, yeah.
Maybe very concrete question related to this one. So if you say, you know you have a separable state, meaning it's this like non-unique convex combination of supposed definite matrices, is the entropy of the coefficient, like the Shannon entropy of the coefficients, like well-defined quantity that doesn't depend on the decomposition? Because you have like a separable state, it's the sum of pi something. Like if you just calculate the Shannon entropy of these pi's, is that well-defined?
I'm not sure, I guess it is, but I would need to write it down.
You'd have to say something about the components, because you could just split one up into two pieces.
I think that's true.
No, and
That's
then
going to change.
yeah. Okay.
I think it's well defined. There's a theorem that says that it's independent of the basis. Yeah, proof is in environmental class transfer.
Okay, so with that we come to purifications on which, okay, Robin explained that in a very different, or to the best of my understanding, you also talked about purifications in a completely different language. And so in quantum theory, both like a fundamental result for the mathematics, like for working every day with such states, are purifications, but it's also of, for me, conceptually, it is very interesting as well. So it says that every mixed state can be purified, that is to say, expressed as the subsystem of a larger pure state. So Okay, maybe I will first say that. So for any mixed state rho S, where S stands for system, there is a pure state in an enlarged state that lives in a larger Hilbert space, psi on SE, where E stands for environment, such that rho S is the partial system, right, of this enlarged global state. So rho S is the partial trace over E of this projector onto this state called a purification. And without loss of generality, psi of SE can be taken to be in CD tensor CD. And for the proof, just take the spectral decomposition of rho S, which is, say, a sum over I from 1 to n of mu I phi projector onto phi I. So mu I are non-negative and phi I are orthonormal. This exists because rho S is positive semi-definite, so in particular Hermitian. And define psi SE as the sum over J of the square root of mu J, which is non-negative, times phi J, so these are these eigenstates, times JE. JE, say, is the computational basis on E. It is immediate to verify that the partial trace of this state is rho S. And it also follows that such an n is at most, so such an n is the rank of rho S, which is at most D. You wrote something very similar earlier, I believe. You had an EJ, tensor EJ, and a square root in front.
I had Formula 9 also. In a case where the phenomenon algebra is just the matrix algebra that you have here, so in D by D matrices, and I had Formula 9 as a specific example.
Okay, so
it's the same thing.
Yeah, so this is what physicists would call the standard purification. And okay, let me make some remarks. First of all, there are infinitely many purifications. So such a purification is highly non-unique. And from this standard purification, all others can be reached by an isometry on the E system. And it is easy to understand that because an isometry, so take just an isometry on the E system will be invisible after the partial trace. So a little more formally, you all know that, but an isometry is like a linear map that preserves inner products. You can think of it as a unitary between spaces of different dimension, say from CD to CR, where R is larger than D. So if you first go to the large space and then to the small space, that's like doing, this is the identity on the small space. But if on the contrary, you start from the big space, go to the small space, and then go back, well, that can only be a projector on the small space. Right? And then the claim is that all purifications have this form. You take this standard purification that we saw earlier, you can apply, and then you apply an isometry on the E system. So every purification has this form for some isometry. And to see that, just note that the isometry is invisible after the partial trace. And to see the other direction, consider two purifications and do the Schmidt decomposition. I think that's what I'm doing here. Yeah, do the Schmidt decomposition on the two purifications. And well, you conclude that the Schmidt coefficients must be the same. And the bases are the same. And so the only thing that is unfixed is the basis on E and here and there. So they could be of a different dimension. Okay, but both are orthonormal bases, so they must be related by an isometry. Essentially, that goes that way. Okay, so I'd like to say a few words about what that conceptually means. So pure states do not describe any actual physical system. They describe an ideal. And it is this result of the purification allows us to describe an actual, like the state of what is supposed to be an actual physical system, that is a system described by a mixed state in terms of the state of an ideal. And also, in contrast to other results in physics that also appeal to an ideal, this one, at least on the face of it, does not involve an infinity. I think it does in some hidden way, but because you have noted that at least in the dimension of this pure state, it is bounded, and it is in fact kind of the same as the dimension of the mixed state. Now, another interpretation that this purification theorem gives us is the fact that we have been seeing mixed states as describing potentially lack of knowledge. Then this is telling us that any lack of knowledge of a system can be attributed to it being entangled with some unaccounted for degrees of freedom, which we can assign to the environment. But such that if we would take into account not only the system, but also those extra degrees of freedom, we would have perfect knowledge of the whole state, because they would be globally in a pure state. But remember that the purification is not unique. Right? There are infinitely many. So there are some interpretational difficulties.
Excuse me, but the sparse isometries, if you ask for them to commute with those observables, then they are unique, right?
Excuse me?
So you have this standard purification,
Yeah.
right? And you have bigger purifications, and you have the sparse isometries connecting the standard ones to the big ones, right? Yeah. If you ask for the sparse isometries to commute with how the algebra of observables are represented in these human spaces, then this sparse isometry is unique, right?
Then you get all the unitaries, or?
You probably cannot expect the actual uniqueness, and we always get uniqueness up to say unitary transformation, and essentially it's the same with the GNS triples that Robin introduced. I don't think you can.
I mean, conceptually, it is like saying that what I just said, the mixed state is entangled with the environment. Right? But the whole thing is in a pure state. Now, if you can only see the mixed state, then you can only say something about these Schmidt coefficients that are entangling both. You cannot say anything about the eigenbases of the environment, which is what these isometries or unitaries are doing. They are changing these eigenbases.
I think the answer what he's asking is on the larger space, the original environment the original measurement operators are the operators that commute with everything coming from the environment. So that's another way that von Neumann algebras show up, because the original measurements are defined as a compound, this new representation.
More comments? Okay, so now I go into very uncomfortable territory for me, but very comfortable for you. So this is here for your pleasure. You understand this a lot better than I do, okay? So let me just read these things, and if you have any questions, maybe you can ask Vern or so. So, and actually we just heard about it, I believe, right?
No?
No?
Special case of that.
Very special case.
Oh. Okay.
Complete positivity.
Yeah, right. Okay.
Special case of this.
Okay. So such a purification is true more generally as expressed by the Stein-Spring dilation theorem. Okay, so in a second we will see that quantum channels are expressed or are described mathematically by completely positive maps. And then we will see that completely positive maps are kind of essentially the same as positive semi-definite matrices via the so-called Choiseul-Miolkowski isomorphism. So maybe that's a bit of a jump now to be talking about completely positive maps, but as I said, this was for your enjoyment. So, okay, it says that every completely positive map phi can be lifted up to a map of the form, okay, now I'm using the star also, V star times that thing V. Okay, so it says that any completely positive map on a C-star algebra A is a composition of two completely positive maps, so that the first is a star representation of A on some auxiliary Hilbert space K, which is followed by an operator of the form, operator map of the form T2V star TV. This second one is, no, is it true? Yeah, I think it's true. It corresponds to the partial trace. Okay, I can read that. If you have A unital C-star algebra, H a Hilbert space, and BH the bounded operators on H, then for every completely positive map from A to B of H, there is a Hilbert space K and a unital star homomorphism called pi, so that this original map can be expressed as V star pi V. So pi is like the purification, right? And V star V is like the compression, which, yeah, in finite dimensions is kind of this partial trace. And furthermore, there is this condition on the norm. Okay, I will leave it here, and we'll move to quantum channels. Yeah. Okay. Okay. So we've been talking about, in some sense, the kinematics of quantum states, which means how they are described, but we haven't said anything about how they should be transformed and how we should describe these transformations, and this will be provided by these quantum channels. And to do so, I'd like to start with transformations of classical probability distributions. Right? So if we take a quantum state given by a positive semi-definite matrix, and we consider only diagonal positive semi-definite matrices, well, they are nothing but classical probability distributions, discrete ones, right? Because in the diagonal you will have non-negative numbers that sum to 1. This is the usual way how people go from quantum to classical, right? They fix a basis and they just express things in that basis. So if everything would commute, quantum would be the same as classical, okay? Okay, so if we have a probability distribution, say on the diagonal of a quantum system, which we can just put now in a vector, what kind of transformations can we apply to it so that result in another probability distribution? Well, they are called stochastic maps, and they are described by non-negative matrices. That is to say, matrices that have a non-negative number in each of its entries, and that satisfy some normalization condition, so that if the sum of these entries was 1, the sum of, it's columns or the rows. So either the columns or the rows need to sum to 1. Okay, these are stochastic matrices. If they also map the all ones to the all ones, then they are doubly stochastic matrices. That would be like the Unitel condition. Okay, for example, the bit flip channel. I don't know if you have, this is a probability distribution, like this one, right? So say that 1 is mapped to 1 with probability 1 minus p, 0, it is symmetric. 1, there's a flip with probability p, then you could describe this transformation by this stochastic map. Okay, quantumly, the most general transformation of a quantum state is described by a so-called quantum channel, curly E here. Curly E is a super operator, that's what people call it, because it maps operators to operators. It's a map from matrices of size D to, say, matrices of size D. What kind of conditions does it need to satisfy? Well, first of all, it must map density matrices to density matrices. So, in particular, positive semi-definite matrices to positive semi-definite matrices. Such maps are called positive preserving. Unfortunately, they are very hard to characterize, but fortunately, quantum channels need to be more than positive preserving, in which case, and they admit an easy characterization. We're going there in a second. For example, so examples of positive maps, well, a unitary rotation, U dagger, this preserves eigenvalues, this does all sorts of nice things. Or a projection onto the first component in the computational basis. That is a positive map, because if rho is positive semi-definite, then so is the outcome. Or the trace of rho times a positive semi-definite matrix like the identity. If rho is positive semi-definite, then its trace is a non-negative number. So we have a multiple of the identity as the outcome, so that's valid, that's okay. Well, that is not a positive map. Its eigenvalues are negative. That would be negative semi-definite if that were positive semi-definite. In particular, positive maps or positivity preserving maps are hermiticity preserving. That is to say, the map applied to the dagger of the state is the same as applying the map to the state and then applying the dagger. This is hermiticity preserving. This is nice because they form a vector space. Hermiticity preserving maps with positive preserving maps form a cone, and they are much harder to characterize. Okay, now there are maps which are positive, but when they are applied to only part of the system, they fail to be positive. And the canonical example, and it's not easy to come up with other examples, is the transpose. Let's denote it by theta. Theta of rho is the transpose in some basis, let's say the computational basis. Now, first of all, note that the transpose is a positive map, because if rho was positive semi-definite, then rho transposed is also positive semi-definite. Remember that rho is complex generally, right? So rho transposed is different than rho. It's Hermitian, not symmetric. But it need not be a positive map, and the simplest example, the canonical one, is our favorite Bell state, the projection onto the Bell state. Remember earlier that the state was 1, 1, 1, 1. If you now apply the partial transpose, that is to say the transpose of only system A, those two ones move here in a flipped way. And this has eigenvalues +1 and -1. This is actually this is the flip operator, and here you can see its eigenvalue -1. So that's not positive semi-definite. So the map theta, the transpose, is positive, but not completely positive, which means that, okay, so let me go here. A map E is n positive if E tensor identity of size n is positive, and it is completely positive if it is n positive for all n. So general transformations are required to be completely positive because they can be applied to any part of a larger system. I always found this condition a little mysterious because it seems to be somewhat extrinsic to the map. Somehow you are asking that the map not only behave well to where it is acting, but that for any possible extension of the map, that also needs to behave well. That means that extension, with a trivial extension, let's say, with the identity, that also needs to be positive. That's what you're asking here. And that's really crucial for quantum channels. Like, quantum channels need to be completely positive maps. Why? Because you must be able to only apply it to part of the system, and that must result in a valid state. So you can never kind of be sure that you're applying it to the whole system. You must have kind of this strength of saying, no matter how small my subsystem is, I am allowed to apply that map there, and it will behave well overall. Something like that. The good news mathematically is that completely positive maps are very easy to characterize in contrast to positive maps. Okay, in addition, it must be trace preserving, not surprisingly. So that is to say the trace of the outcome of the map must be the same as the trace of rho for every matrix. For example, a unitary transformation is trace preserving because the trace is cyclic. But that projection onto the first component of rho that we saw earlier is not trace preserving, because say that rho is 2 by 2, then there is some weight on the 1 that is lost after this projection. So that's not trace preserving. This one is not trace preserving because the identity is not normalized. If it were normalized, it would be trace preserving. This is not trace preserving either because it's minus the trace. So a quantum channel is a completely positive trace preserving linear map. Examples. So let's say rho to the trace of rho times z, well, it's not a positive map because z has a negative eigenvalue, not a quantum channel. Rho to rho plus identity, not trace preserving. Rho to rho transposed, not completely positive. A unitary evolution has it all. It is a quantum channel. But this is not the most general form of a quantum channel, as we will see shortly. Someone asked that yesterday about the unitary evolution versus the measurement. So that is a valid transformation of a quantum state, as you might expect. Now, if rho goes to the projection onto the first component plus the projection onto the one component, that's a valid quantum channel. As we will see in a second, this is in fact the Krause decomposition of the quantum channel, and it is trace preserving. because it's keeping all the weight that was on the diagonal. And this is called the pinching map. It is a map that kills all the coherencies, if you like. So it kills whatever was outside of the diagonal. Or if rho goes to the trace of rho times the normalized identity, that's also a quantum channel. This is called the completely depolarizing map. It is the map that completely erases the information of your input density matrix, other than the trace, but the trace was supposed to be 1, and outputs the maximally mixed state. So in some sense, it's like the map that's the noisiest of all, most non-injective, most rubbish. Like there's no, you see, like every point in the domain goes to a single point in the image, which is the most useless state. Or such a thing. Rho goes to a convex combination of P times, say, Z rho Z. In fact, it's Z dagger, but Z dagger equals Z. Z is Hermitian. So we have a convex combination of Z rho Z dagger plus 1 minus P of the completely depolarizing map. This is also fine. It is trace preserving. And as we will see in a second, in fact, this is the Krauss decomposition of the map. So completely positive maps admit a Krauss decomposition. That is to say, they can all be expressed as a convex combination of a matrix, let's say AK times your input matrix, and on the back you need AK dagger. Okay, so first note that if rho is positive semi-definite, then if you combine it with, if you go like A rho A dagger, that's also positive semi-definite. Is this true? Yeah, that's true. Yeah. Okay, so that's positive semi-definite, that's good. And if you have like a convex sum of such things, that's also good. But of course the statement is a lot stronger. It's saying that every completely positive map is of this form. And this follows essentially from the purification of the map. And maybe we go through these examples and then we finish for today. I feel that people are a bit tired. Yeah, it follows from the purification of the map into a unitary map in a larger space, or equivalently from the purification of a positive semi-definite matrix and the Choi-Jamil-Coves isomorphism. And AK are called the Krauss operators of the map, and in some sense are nothing but so when you have a positive semi-definite matrix like rho, you can express it as B dagger B. These B dagger, or each of these, there's some change of rows and columns. I don't know if it's now the columns or the rows of B, become these Krauss operators of the map. So this Krauss decomposition of the map is essentially the same as expressing a positive semi-definite matrix as B dagger B. Okay, so examples, rho goes to something like that, normalized, that's okay, quantum channel, or a convex combination of flipping rho plus doing a phase flip. But something like that where R is not Hermitian, is not a quantum channel, something like that is okay. And maybe I finish. Can I finish? Or is that too much? I think people are hungry. I can finish here. I can leave it here if you like.
Yes, you have to stop or
do you want to go for like 3 more minutes or not?
we can surely do 3 minutes.
Okay, 3. I promise. It's only 3. Okay, so So this is the bit flip channel. This is the depolarizing channel, where you kind of, with a certain probability, you get an error in the X or the Y or the Z direction, and with the remaining probability, nothing happens. And the other one is the completely depolarizing map. Some remarks. The composition of the quantum channels is a quantum channel, so they form a semigroup, but the identity is also a quantum channel, so they form a monoid. The only quantum channels that can be inverted as quantum channels are unitaries. All the rest, kind of their image is non-injective, or like smaller than the outgoing set, and they cannot be inverted as quantum channels. Positive maps are very hard to characterize. If the partial transpose of the state is not positive semi-definite, then you can conclude that the state is entangled. So negative partial transpose implies entangled. The converse is only true in 2 times 3 dimensions. That's the Perez-Horodesky criterion. Okay, I hope this is right by the Choi-Effers theorem, but here there are some people who know a lot more than that.
Just Choi.
Just Choi?
We can
Okay, no.
we shouldn't forget that.
Only Choi. Complete positivity. Okay, so that's also interesting. In principle, you would imagine that complete positivity, because it's like an infinite set of conditions, right? You need to check that for any extension of the identity, the map is positive. But fortunately, we don't need to resort to infinity, like a finite. Is this right? I think this square is right.
Should be n.
Sorry. So depending on whether n is the size of the matrix or the other, I always mix this up. Sorry about that. Okay, this is wrong. No squared, okay? No squared. So you only need to check the extension up to a size which is precisely the same as the size of E. Okay. So if it is positive for all those sizes, then it will be positive for all larger sizes as well. Okay, now a linear map E is unital if it maps the identity to the identity. And of course, in the Krauss decomposition that we saw earlier, well, that results in this condition. If we had here the identity, and then that must be the identity. Now, trace preserving and unital are like dual conditions. In the Schrödinger picture, so the expectation value of an observable is trace of O times rho. In the Schrödinger picture, the state evolves and the observable does not. And then E is required to be trace preserving. In the Heisenberg picture, the observable evolves. In that case, E star must be unital. So E is trace preserving if and only if E star is unital. And that's physically, it's like changing from the Heisenberg, from the Schrödinger to the Heisenberg picture. It doesn't matter which picture you choose because you can only see expectation values of observables. It's kind of an internal symmetry of the theory. This equality here. The Stein-Spring decomposition, the Krauss decomposition can be derived from the Stein-Spring dilation of the channel. So here I am just saying that these AK are essentially the big unitary projected onto a certain basis for the environment. And that's it. Thank you.
Yes, I will just.
Yeah, okay. A quick one. So if you can go up to your list of quantum channels, there was one that I thought was not a quantum channel, and I want to check what a little bit higher, right? That I really should have interpreted as a quantum channel. So you have rho to AK rho AKs are divided by the trace, but that's not a linear map, right? If I would multiply rho by 2, nothing changes.
Last one.
Denominator.
Maybe you're right.
So I just wanted to check that there is no way that you interpret this as a function channel, right?
I agree.
Maybe you're right, and I'm wrong.
I think the dividing by the trace, I think is there for a normalization, but I think you just want the row out of there.
Yes.
Yeah, yeah, you're right.
It's just dividing by this constant to make it normalized. Yeah.
But then it won't be traced.
By the way, another thing I forgot to say is that I don't know what the faithful or normal condition in translates.
All of this is normal.
In finite dimensions, the normal doesn't mean anything.
So
But doesn't it mean that it's non-zero or something like that?
Normal is just nothing. But faithful is
Faithful. What does it mean?
that none of Rho's eigenvalues is zero. They are all strictly greater than zero.
Yeah, that's a little weird.
So the maximally mixed state will always have this property.
Yes, but rho can be rank efficient and it can be purified.
we're not saying it cannot be.
Okay, maybe we'll stop here, but.